In this video, we will be analyzing the motion of a yellow playpen ball with an average size of 8.89 millimeters and an average mass of 0.37 kilograms. We will be looking at this playpen ball to see if the Newton's second law of motion can be used accurately in computational models to efficiently predict the future. First, after recording the video, I inputted it into Tracker to get the data from the motion of the ball. As you can see, the points moving along the points that show the ball's location, matching up with the chart of data over here and the graph line over here. I set up the XY axis to go along the motion of the ball in the negative X direction. It would not matter if I switch the axis to the Y direction. Either way, the ball would still be moving to the left direction of the screen and the data would come out similar. As I am doing this, I am using the physics adaptation of Newton's second law, V final or Vf equals V initial or Vi plus the net amount of forces over mass, F net over m, times the delta t, which is the change in time. I then use that physics adaptation in VPython, where I input all the data that I obtained from Tracker, such as the experiment, which is the ball's mass, 0.37 kilograms, the ball's initial position given to me by Tracker, and the ball's initial velocity, which is also given to me by the data in Tracker, but I have to figure it out using simple mathematics. Here, as you can see, if I take the second position and the first position and subtract it from the second position, and this first time subtract it from the second time, then I divide the first the position by the time, then I get 0.55 as the initial velocity. I then insert the last time that the data goes up to in order to stop the loop at this time to keep the data congruent with one another. As I run this computational model, you can see that it looks fairly similar, but it is not all up to looks. We have to compare the actual data that comes from it. In order to compare the data, I have inputted it into a Google Doc spreadsheet. As you can see here, this is the experiment positions and this is the model positions. When inputting the data in the chart, as you can see here, the data is very similar in the beginning, but at a certain point it starts to deviate from each other. The experiment data starts to change in velocity as the model data, which is based on the constant no net force input that I gave the computer, stays constant and goes down in a stream. This is where the experiment data should be under ideal situations, but due to human error and certain forces that cannot be controlled, there is a slight change in the flow of the chart. Thus, here you can see that the computer has a very good system of using Newton's second law to predict real-world situations under the right computational circumstances. But here, the experiment was not under the same constant motion that the computer has in the perfect situation, so it is not a perfect lineup, although it does show that to answer the initial question, computational models can use Newton's second law efficiently to predict the future in real-world situations. Thank you for taking the time to watch this video.